Hello everyone. Thank you very much for having me today. My name is Arda Senocak. I'm a PhD student in RCV lab at KAIST Korea. Today, I will talk about player identification in broadcast sports videos, its challenges, and how we can overcome these challenges. The work that I'm going to talk about today was presented at Computer Vision in Sports Workshop at CVPR 2018 as an oral paper. My collaborators in this work are Tae-yeon Oh, Junshik Kim, and In-so Kwon. Tae-yeon Oh is assistant professor at POSTECH right now. Sports video analysis has a wide attention and have many commercial applications. This is not only interest of coaches and sports scientists, but also media companies want to provide all sorts of performance statistics to their viewers. To this end, computer vision has recently started to play an important role in sports. Automatic player detection, tracking, and identification are some of the major applications for enhancing broadcast sports videos. Even though detection and tracking algorithms are getting advanced, some of the commercial tracking systems still rely on manual or semi-supported player labeling. Also, many of the tracking algorithms cannot follow the players continuously because of some interruptions. So when that happens, we should reinitialize the process. It means we should relabel the players. That's why fully automated player identification at a given moment in time is very important and open challenge. If we think about ourselves as a human being, we can easily recognize the players in the field. But can machines also do that? So in this work, we try to focus on this problem. But before starting to our work, if we look at the previous approaches in the field, they are mostly concentrated on close-up camera views rather than broadcast views, so that they can easily detect and recognize faces or jersey numbers for player identification. However, this is not really realistic because we don't watch the games in close-up views. Broadcast view is the most common camera view on sports videos. The first attempt to solve this task in broadcast camera view was a work in 2011, which is before recent developments in machine learning and computer vision, such as deep learning, so performance is not satisfying. Considering all these previous works and the problems, our work is the first attempt to solve player identification task in broadcast views with deep learning. Okay, but what are the challenges broadcast view brings into this task? First of all, distinctive features such as faces become blurry or not visible. Jersey numbers are deformed or not seen in every frame. This shows that concentrating on faces or jersey numbers, as in previous works, are not the optimal solutions. Also, appearance of the players look almost identical. For example, first three images belong to three different players. And lastly, body pose and postures might look unnatural, so it makes identification difficult. Considering all these challenges, how can we design our system? In order to deal with similar appearance of the players, we use the entire body of the players and body parts separately. The system has two main modules. One deals with the entire body representation, and the other one is for body parts representation. Let's start with the entire body representation first. To capture small differences between the players, we use multi-scale images up to 7 scales, starting from small to big. Then, each scale image is fed into image encoder. We used AIX as an image encoder here, but you can use any other network architecture. And we also replaced the fully connected layers with convolutional layers so that we can get multiple activations for each scaled image based on their size. Once we get the activations at each scale, then we aggregated activations at each scale independently by using Fisher vectors. Fisher vector is another design choice here. You can use more recent methods such as netflat. And now Now, we have one fixed length Fisher vector for each scale. Then we apply average pooling and had final body representation. As a first approach, we used these entire body features and learned linear classifier to identify the players. While doing this, we were curious what makes a player a player. It would be really interesting to analyze what makes that player particularly different from the other players. So for example, here, we get small patches by moving around in the James Harden's image and ask the machine, is this patch belong to Harden? If it is yes, then we accumulated some score in that part. So here we use the linear classifier that we learned in the previous slide that I mentioned. So we can get some attention map about distinctive parts for Harden. Then we applied this technique to all of the players, and we got some attention maps for each player that shows which information was useful to identify them. When we look at the results, distinctive details appear consistently on similar locations for each players. For example, for James Harden, important parts are always his beard and sleeves on the knees, because James Harden is the only one who has a long beard in the entire team. Similarly, socks, shoes, sleeves, jersey numbers, and head parts look like distinctive parts for the players. For Beverly, shoes are very distinctive because he's the only one who has white dominant shoes. Or if you look at the Jones, his long sleeves are distinctive. So we can easily see that our algorithm can automatically capture face and jersey numbers, even though we didn't teach them separately as in the previous works. So we see that these distinctive parts are most of the time are not covered by the jersey. So somehow, if we can get some information from those parts, then our player representation will be more complete. That's why we proposed body part representation module. Body part representation module only takes single scale image, and then it uses convolutional pose machine to locate the body parts. Once we locate the body parts, then activations are extracted from every part by feeding them into the encoder. Once we get the activations, we aggregated all of them into one single Fisher vector that represents the body parts. So the final player representation is the concatenation of the entire body and body parts representation. After that, we learn linear classifier to identify the players. Let's look at what kind of data we use in this work. While we were doing this work, there was no publicly available dataset with the corresponding player detections and identities. So we collected a new dataset from 2015 Denver Nuggets versus Houston Rockets game for training and testing. We asked the human annotators to draw bounding boxes around the players and tag them in regularly sampled consecutive frames. Since this takes a huge amount of time, we only focused on the starting 5 players of the Houston Rockets. And we used the first half of the game for training and the second half for testing. And once we get this training data set, then we use 2,500 samples for each player to learn the classifier. This is our performance table. We applied our work only on starting 5 members of Houston Rockets, as I mentioned before. And we ignore the temporal information between detections. So identification is done per frame to check we can successfully identify the players or not at any random time. First 3 approaches in this table are very typical image classification methods in computer vision. And dense sift and bag of words method is very classical computer vision method before deep learning times. And the last 2 rows are the 2 methods that we proposed in our work. As expected, classical method performs the worst, and our combined method gives the best performance. One interesting observation was Motiejunas always gets higher accuracy than other players in every method. We believe that the color information helps to distinguish him because he's the only Caucasian white player in the Houston Rockets team. Also, we see that Harden, Beverly, and Ariza are the players who mostly benefit from our part-based combined method. However, Motiejunas doesn't, because Motiejunas doesn't have much discriminative parts. If we look at this figure again, Ariza, Beverly, Harden, and Jones, they all have some strong activations in their attention maps. However, if you look at the Motiejunas, it has relatively weaker signals than the other players. So that's why it doesn't get benefit much from the combined method. Before finishing my talk, I would like to show some results on video clips. So in these videos, you will see some green and red boxes. Green box represents correct identification and red color shows misidentification. Again, we didn't use any temporal information. Results are per frame identification. And this is another video. And this is the last video. In this video, you might see that in some time, we don't run our algorithm because those are mostly the close-up camera views. So we only run our algorithm in broadcast views. Such as in this case, this is a very close-up camera view, so our algorithm is not applied to these kind of scenes. But once the view becomes broadcast view again, our algorithm can successfully run. And lastly, our system also allows us to create virtual star view camera for interested player. Since we know who is who on the court, virtual camera angle can be created for your favorite player. Let's watch our application. In this video, we created virtual zoom camera for every player in the white team. For example, if your favorite player is number 32, then you can watch her entire game with the virtual camera that we created. But here our favorite players keep changing, so you will see different virtual cameras for each player. So to wrap up my talk, this work focuses on player identification in broadcast view videos at any given moment in time. It is completely data-driven approach, so it doesn't require any device or hardware, and it can be easily extended to other teams or any other basketball video on the internet. Of course, player identification is not the only important application. Computer vision algorithms have a huge potential in many aspects of sports, from tracking players and objects, activity recognition, performance analysis, to enhanced viewing. So it is very important focusing on computer vision-based research in sports. Thank you very much.